Hello everyone. SciencePod is a podcast that shines a spotlight on the latest scientific technology from Japan. Your host is Ran from SCIEN-TALK. Today's SciencePod, we're going to focus on world's whitest paint, developed by Purdue University in the United States. And today's episode is part of the monthly Science Podcast Day. Our topic for this discussion is color. So why is this paint attracting so much attention? While conventional white paints typically reflect only 80% to 90% of sunlight, this paint boasts an astonishing ability to reflect 98.1% of solar radiation. Imagine a building becoming a super mirror that almost completely deflects sunlight. What's even more crucial is its innovative cooling ability. It can keep the coated surface cooler than the ambient air temperature. Global warming is one of the most pressing challenges facing modern society. This paint is regarded as having immense potential as a passive cooling technology, offering an alternative to active cooling system like air conditioners that consume electricity. It's like envisioning buildings themselves starting to breathe cool air. This technology is expected to significantly reduce electricity consumption and associated carbon emissions, thereby contributing to the realization of a sustainable society. Now, let's explore why this paint is not just incredibly white, but also capable of cooling. This secret lies in its composition and the cooling mechanism. The main component of the initial this version is barium sulfate. While this is a common white pigment used to photographic paper and cosmetics, the key to this paint's effectiveness is the different size distribution of its particles. Imagine various-sized pinballs bouncing light in different directions. Similarly, different-sized barium sulfate particles efficiently scatter a wide range of solar wavelengths, including ultraviolet, visible, and near-infrared light, achieving that incredible 98.1% reflectivity. Unlike titanium dioxide pigments typically used in conventional paints, which absorb UV light and heat up surface, but barium sulfate absorbs almost no UV light, enabling its superior cooling performance. And the most revolutionary cooling mechanism of this paint is known as passive radioactive cooling. This technology not only reflects sunlight with extremely high efficiency, but also simultaneously actively emits infrared heat from the coated surface directly into outer space. It's as if the building has a special heat vent designed to release warmth toward the cosmos. The emitted infrared radiation is specifically engineered to match a particular wavelength range known as the sky window, 8 to 13 micrometer, which the atmosphere is transparent to. This allows the heat to propagate efficiently directly into the ultra-cold deep space without being absorbed by our atmosphere. Though this mechanism, the paint emits more heat than it absorbs from the sun, consequently allowing the coated surface's temperature to drop below the ambient air temperature. This fundamentally distinguishes it from conventional paints that merely block heat. The actual cooling performance is remarkable. Outdoor tests have demonstrated that even under direct sunlight during the day, the coated surface remains up to 4.5 degrees Celsius cooler than the ambient temperature. Furthermore, at night, it can be maintain a surface temperature that is up to 10.5 degrees Celsius lower than the surrounding air. This is a huge benefit for regions suffering from heat waves during hot summer nights. And notably, reports indicated that even in outdoor tests conducted in cold temperature for approximately 6 degrees Celsius during winter. This paint continues to evolve, and the Purdue University has developed a thinner, lighter new formulation aiming for application in transportation equipment where weight directly impacts performance, such as aircraft, automobile, and trains. This new version used the hexagonal boron nitride as the primary pigment, which is about half the density of barium sulfate, making the entire paint 80% lighter. It also achieves a 97.9% solar reflectance with a very thin film thickness, about 150 micrometers. The applications of this paint extended beyond just building roofs and the exterior walls. In addition to the aircraft, automobiles, and the trains we just mentioned, and the professor is also considering its application to clothing, shoes, and even portable electronic devices like mobile phones. And imagine wearing clothes that keep you cool in summer, or smartphones that maintain optimal temperature even under heavy use. This truly points to the future where heat management solutions become ubiquitous in every aspect of our lives. The environmental impact is also immeasurable. According to statistical models conducted by Purdue University researchers, applying this paint in hot US cities is estimated to reduce air conditioning usage by up to 70%. This not only saves us money on electricity bills, but also suppresses the burning of fossil fuels for power generation, thereby directly reducing carbon dioxide emissions. Moreover, extreme simulation by researchers estimate that covering just 0.5% to 1% of the Earth's surface, and with this ultra-white paint would be sufficient to halt the trend of global warming. This area is vast, equivalent to slightly more than half of the Sahara Desert, but it illustrates the potential scale of its impact. However, it's important to remember that experts from the University of California, Davis have raised significant concerns that covering such a vast area could threaten wildlife and disrupt weather patterns, underscoring the necessity of careful evaluation for large-scale implementation. So this world's whitest paint is not just a technology with record-breaking performance. It holds immense potential to contribute to reducing the energy consumption in our daily lives and combating global warming on a planetary scale. Currently, corporate partnership and patent application for commercialization are underway, and while a widespread market release specific product hasn't been confirmed as 2025. So the focus of research and development is shifting from mere performance maximization to solving real-world challenges. That's all for today's Science Put, and as I mentioned at the beginning, this episode is a special contribution to the Science Podcast Day event. If you are interested in science discussion in Japanese, please check out other podcasts from the links in the description box. This podcast is broadcast daily on weekday morning in both Japanese and English. I'd love for you to listen to the podcast and post your notes and thoughts with the hashtag SciencePod. Thank you for listening. See you next time.